Hello, my name is Jobin Joseph, and I'm going to be talking to you today about hidden Markov models, HMMS, and utilizing the Baum-Welch algorithm. I'm doing this part of my Machine Learning 2 class for a final project. So for the agenda today, I'm going to be talking about the origins of the Markov models, talk into the overview of a Markov model, give an overview of the hidden Markov models, have an example of a hidden Markov model, overview of a Baum-Welch algorithm that is used to calculate in a hidden Markov model, and lastly, talk about applications that you can use these algorithms and models in. So the origins of the hidden Markov model. Originally, the law of large numbers allowed a normal distribution to be formed, was one of the main theories in statistics. Pavel Nekrasov argued that being able to determine results only worked with independent variables. Andrei Markov disagreed and was able to find out that and create the Markov chains to explain why the law of large numbers can also apply to dependent variables. So if you look here, this is a picture of Andrei Markov. He was from around 1856 to 1922, and he was a Russian mathematician who taught probability theory at the University of St. Petersburg. So an overview of what a Markov model is. So Markov works by Markov chains work by quantifying the likelihoodness of transitioning between states. There are different types of Markov chains. If you look here, there's two states, and it can give you the probability of transitioning into another state, or like there's 70% or 40, like that. They can show you what it could transform to. So there's some rules. One is like they should be equal to 1. So you see 0.3, 0.7 is equal to 1%, total 100%. So yeah, in another way, Markov chains or Markov processes is a stochastic model describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. So it does look back into where it originated from to show you possibly where it's going to. For example, this is an Markov model here. So we are looking at 3 different foods and seeing, like, for example, a lunchroom, and seeing what will be the food of the day. So you can see that based on what had occurred the day before, you can see that there's a 0.3 30% chance of becoming a hamburger next day, or a 70% chance of having a hot dog for lunch the next day, and both of that equals to 1. Or if you have a hamburger, you have a 20% chance of having a hamburger the next day. So this is like a simple Markov chain. Next, this is a example of a hidden Markov chain. This hidden Markov chain represents a 2 variables, mood and weather. So, for example, we can have a story where this person named Joe lives in a town, and we only know about his moods, but we do not know about the weather. So we have sad Joe, happy Joe, and the 3 types of weather, rainy, cloudy, and sunny. But we only know that he's happy or sad on a given day. There's a 80% chance, by looking at this Markov chain, you can see there's a 80% chance that Joe is happy when it is sunny outside by following this line here. Or Joe is sad, there's a 90% chance that it is raining outside. So in this case, the weather is the hidden state, as we do not know what the weather is as an observer. But these 2 moods are what we have observed and we do know. So Joe's mood is the observed variable in this, which we can see. And it is important to note Joe's mood only depends on the days of the weather, but not his previous day's weather. So this is directly correlated to whatever weather it is that day. It's not talking about what the weather is the previous day. In this diagram, the green arrows would represent the transition probabilities, and the red arrows would represent the emission probabilities. So we can say that there is transitioning going on here based on what the weather is one day to what the weather will be the next day. So that is part of the Markov chain, but we can't see that that you can't observe what it is. So you're going on the link between what the weather is and what the output is. So even though you don't know what the weather is the day before, using the Markov chain, you can see the transition probabilities and see how that would affect that observed variable. So overview for the hidden Markov models. There are some important definitions to know, especially for hidden Markov models. There's the emission probabilities, the conditional distribution of observations in the given states, and transition probabilities, which is the prior distribution of hidden states. In other words, we can see that emission probabilities deal with observations that are noted, and the probabilities that explain the transition to and from the hidden states are the transition probabilities. Next, during my project, when I was looking at the hidden Markov models, there was, when I brought it up in class, I was told to look into the Baum-Welch algorithm. So looking into the Baum-Welch algorithm, it is also known as the forward-backward algorithm. The Baum-Welch algorithm is a dynamic programming approach, and it uses a special case of the expectation maximization algorithm. And you can see that you are looking to see for the parameters of lambda, and using this, using a recursive process, you can see to try to find a local maxima or minima, but you're not guaranteed to get the global maximum or minimum. So there's a few phases of this algorithm, including the initial phase, the forward phase, the backward phase, and the update phase. The forward and backward phase form the E step of the EM algorithm, while the update phase itself is in the M step. The result is that it converges to a stable good answer, but it might not be the best as it searches for a local optimal result, as it solves for parameters for lambda. This is kind of like a gradient descent in a way in which it's a iterative process. So we can see by doing it multiple times, we're getting closer and closer to the local optima. So you can see here, the forward and backward phase is part of the E step, and the update phase is part of the M step. So hidden Markov models are used in a wide variety of use cases. So you can use it for bioinformatics, for single molecular kinetic analysis, gene prediction, protein folding, DNA motif discovery, DNA hybridization kinetics, just to name a few. You can also use it for NLP, for speech recognition, speech synthesis, part of speech tagging or POS, and document separation. And finally, you can use it for other fields such as computational finance to try to see links between a cause and effect. And these are my sources. And thank you for listening about the hidden Markov models and the Baum-Welch algorithm.